Relativity is often misunderstood due to its counterintuitive concepts. In today's video, we are going to debunk some of the most common misconceptions about special and general relativity. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome in learning what are the common misconceptions about relativity. The first misconception starts in understanding special and general relativity. What are those concepts and misconceptions? Let us look in the next part of our video. Now, it is often understood that a common misconception is that special and general relativity are entirely separate theories, whereas the fact is that special relativity is actually a subset of general relativity. Many think special relativity and general relativity as unrelated, whereas GR is an extension of special relativity, incorporating gravity in the relativistic framework. In special relativity, we deal with something which is called inertial frames of reference, which deals with generally high velocities, etc. Now, what do we mean by inertial frames of reference? Here are a few of the concepts. Number one, when we talk of inertial frame of reference, we mean to say that there is a frame and this frame is moving at a constant velocity. The important part is that there is no acceleration. Point number two, forces. When we talk of forces, inertial frames of reference, there is no fictitious or pseudo forces that appear. Third is that the Newton's law, the first, second and the third law, holds in their standard form. For example, a spaceship is moving at a constant speed in a deep space. Now, when I talk or when I say that Newton's law hold in their standard form, this requires a little bit of modification. This requires a little bit of better understanding in terms of special relativity, how these concepts have been modified. Well, in general, Newton's law originally formulated from what are called classical mechanics, and they assume three important things. First is that there is an absolute time. That means it is same for all observers. It is a grand clock of nature which is going on and on and on. There is another concept which is assumed to be, which is called absolute space. That means same distance measurement for all observers. And third, a little bit mathematical, which is called the Galilean relativity, where velocities simply add up. So if you're a person walking inside a moving train which has got a velocity of 10 plus 20, it will just add up and it will give you 30. That means the velocity is equal to the sum of your walking speed and the train speed. However, special theory of relativity modifies these ideas, but remember, they do not really invalidate Newton's laws in their domain of applicability. So sometimes you come across blogs and websites and videos which tells that Einstein proved Newton wrong. No. It at all does not prove anything wrong or anything right, but it modifies and makes the theory better so that it is applicable in certain high speeds, velocities, etc. So the first thing is that the first law, that is that an object moves in uniform motion and remains in uniform motion unless acted upon by force, this holds very well. So this holds in both Newtonian and relativistic mechanics, yes, but we have to assume that it is in an inertial frame of reference. What we mean by inertial frame of reference, we have understood that. So that means that relativity only modifies how we measure motions at very high speeds, but the fundamental principle of inertia remains the same. So the first law, we see that it is applicable both to Newtonian and relativistic mechanics, provided we remain in an inertial frame. And the most important note is that nothing is wrong, it only modifies, and the fundamental principle of inertia remains the same. How it is, let us look in the next part of our video. In classical mechanics, as we know, Newton's second law can be written in two equivalent forms. The first one is force equal to mass times acceleration. Since m is constant, we can differentiate and we can write this or we can write this. So what we can say in classical mechanics, force is indeed the rate of change of momentum, and this reduces to F equals to ma. As you can see here, mass is constant. Now, in special relativity, mass is not strictly constant, and what we get is something which is called this one. Here you can see that this is something, a new factor, the gamma factor, which we will learn later. This is called a Lorentz factor. You can just assume Lorentz factor is a kind of a mathematical calculation which will keep things as per the high speed or motion. We see here that mass, this is the rest mass and v is the velocity. So from here we can see that p or rho equal to mass times velocity. This is the classical Newtonian momentum, and here we get the relativistic momentum where the same mass, where the same velocity is there, but there is a correction factor which is called the Lorentz factor. So what we get from here is that this gamma is because relativistic effects modify how momentum behaves at high speeds. We are not looking in the mathematical derivation, but let us understand that in special relativity we need a gamma factor. So this gamma is there because relativistic effects modify how momentum behaves at high speeds. Mass, as you can see, still is the same, rest mass. We are just correcting the classical formula to match relativistic physics, and momentum remains conserved in all frames with the gamma correction. But here I would like to say that this gamma in special relativity is not typically a mass times velocity. It has got something which is called a form momentum. That means the momentum in the x direction, y direction, z direction, followed by the speed of light. Now all of them has been encoded, or it has been taken into account with the single gamma factor, which actually ensures that all the components of the form momentum transforms consistently under special relativity. So the first misconception which arises is that mass and velocity, how they're related. So they are related by one correction factor, which is the Lorentz factor, which is the gamma factor. And this gamma factor is not a typical momentum, but it is called a form momentum. Now, in case that you're interested to know more about form momentum, you can go just to my last week's video, Spacetime, Curvature and General Relativity, where I have discussed actually where this form momentum comes from. Where are the limitations or vectors and how it leads to form momentum, and from there the tensors, etc. So form momentum is something very specific which actually generalizes the typical Newtonian vectors into what are called four vectors and into form momentum, for force and so on. This video will speak on this. However, what we can see from here is an important misconception. That is what is called this one. Now here you get a concept which is called a rest mass. Now this is the invariant mass. That means it is the same for all frames of reference. In general, what we commonly call mass in classical mechanics and in modern relativity, it is sometimes denoted by m with a little zero at the bottom, but this is what is called the rest mass. Now in some older textbooks which you can see, it is referred to as this. M-rel means relativistic mass, and something which is not written is basically called classical mass. That is the rest mass. But you need to understand one thing. This suggests that mass increases with velocity, but this is misleading. Indeed, mass increases with velocity, but you have to understand that modern physics does not use this concept because it leads to various other confusion. So we really do not talk of what is called a rest mass. Instead of thinking what is called a rest mass, we describe relativistic effects through what is called a momentum and an energy. What do we mean by that? So we have got our relativistic momentum, which we understand, and then we have got a relativistic energy, which is the famous E equals to mc squared. Both of them has got a gamma factor, which is the Lorentz factor, and this actually tells that in modern physics, mass does not increase with velocity. Rather, we term it as momentum and energy behave relativistically. So using the relativistic mass F equals to ma might lead to confusion because the acceleration also depends on direction. In modern physics, we only talk about rest mass. We only talk about rest mass m, and we incorporate relativistic effects into momentum and energy instead of what we call mass. So from here we can understand this is a very important concept, that if you take a rest mass, then it is same in all frames of reference. This is an intrinsic property of an object and does not change. Whereas momentum increases with velocity, and that is why we got the gamma factor. But this is due to this one, the gamma factor, but not because of mass. This is important. Momentum increases with velocity, but this is due to the gamma factor in P equals to gamma mv, not because of mass. Energy increases with velocity. Total energy is given by this, but mass always remains fixed. So instead of saying that, we can say that instead of saying mass increases with velocity, in modern physics we describe the situation correctly by saying momentum and energy behave relativistically while mass remains constant. This is a very important feature. This is a very important note which most of the people they might miss, is this one, that it is momentum and energy behave relativistically while mass remains constant. So we are not at all confused with what is called the rest mass, etc. Well, so far so good. Now energy, when we are taking a kind of a block, or say for any object, we can say that energy approaches, so velocity is moving close to the speed of light, and what happens is that the momentum approaches infinity as velocity approaches, so this gamma factor increases and keeps on increasing. Now when we say that it keeps on increasing, I would like to show you an analogy. So suppose you are moving at 10% close to the speed of light. By doing the Lorentz factor, we get something like 1.005, which is almost no effect. If we take 90% to the speed of light, the gamma factor shows close to 2.3. Well, yes, it is a very big effect. And if you run close to the speed of 99.999999% of the speed of the light, then the gamma factor is 70.7. That means that it has got a huge effect. So again, to tell that instead of saying mass increases, we say that energy approaches infinity as velocity approaches close to the speed of light. Momentum approaches infinity as a velocity approaches c, but the mass remains unchanged. And as v approaches c, you can see now how the gamma factor changes. Now this actually causes momentum and energy to increase rapidly. Let us look at the next part of the video, if you can say it very cleanly. So we can say that an object which has got a non-zero rest mass can never approach close to the speed of light. That is true. And energy, as energy approaches infinity, here also the velocity approaches c, but remember, mass remains unchanged. So from here, what we can say that in special relativity, we know that momentum is given by this, where p is the momentum, m is the mass, again the rest mass, v is the velocity, and gamma is the Lorentz factor, which is given out of this. Don't worry if you don't understand how this 1 upon v squared c squared came upon. It is not a big issue. The most important factor is that this, what happens when v approaches c? We have seen velocity is closing to the speed of light and the gamma factor is increasing. So in case we take this Lorentz factor and we put in the same relativistic momentum equation, then what we get is this one. And as you can see, as v approaches c, we get v squared c squared equals to 1, and we substitute, the denominator cancels out here, and as the denominator approaches 0, it becomes indefinite, or the fraction blows up to infinity. So from here, what we can say, as momentum approaches infinity, velocity approaches close to the speed of light, and an object with mass cannot reach the speed of light because its momentum becomes infinite, as you have seen in the calculation, requiring infinite force to accelerate it further and further. So these are few of the concepts in terms of understanding special and general relativity, especially not to think mass as a rest mass, but rather to think in this pattern. The next misconception, or rather the confusion, arises in understanding what is called a flat spacetime and a curved spacetime. Now in flat spacetime, in the realm of special relativity where gravity is absent, you can see that the light cone has got all these straight lines. So the motion follows simply straight line paths. But in general relativity, due to the curved curvature, due to the presence of mass and object, there is a curved path. So if I take a sphere and point out a red dot over here, we can say that it actually follows a straight line, but due to the curvature, this motion is appearing to be curved. So when mass and energy is present, the curved space-time, the objects move along geodesics, which are technically called the straightest possible paths in the curved geometry. Now as we turn the page, we can understand this in a little bit more subtle manner. So if I get an object over here, and if I try to move this object, I am trying to move this object, rather the object is itself accelerating from here to here. Again, as I show you, from here to here. So if an object or an observer is moving from outside, what he finds is that the particle is accelerating. There is some external force which is causing the particle to move. But the fact is that it is not. It arises naturally from the curvature of space-time. That means this acceleration is not any kind of a force in the Newtonian sense, but it is just the curvature. And the particle is following the straight line, but the curvature is making it follow in a curved path. So here are a few of the misconceptions which arises that curved space-time means physically bending like a sheet of paper. No. The curvature happens in 4 dimensions. It is not just space, it is the entire continuum. Space-time itself bends. Now, objects do feel a force pulling them down in a gravitational field, just as the observer here has observed. No, objects actually move in natural paths in curved space-time. And some people think that general relativity is only about black holes and neutron stars and very extreme conditions. No, even the Earth and Sun curve space-time, affecting everything from the GPS signals to planetary orbits. So you know that the misconceptions arise when we try to think gravity as a force rather than it should be understood as a geometric effect of space-time curvature. Here is a tabular diagram which will make things easier. So if you take the metric in flat space-time, it is a Minkowski flat metric. Here it is got Schwarzschild, Kerr and various other metrics. The feature in terms of gravity is that it has got no gravity. Here gravity is a structure of space-time or a curvature of space-time. Geodesics are straight lines. Here it is curved paths, and time dilation here is due to velocity, and here it is both due to velocity and gravitational field. Well, what does it actually mean, velocity and gravitational field? Let us look in the next part of our video. What do we mean by time dilation and gravitational time dilation? Now in this case, I would like you to imagine this kind of a tick-tock, tick-tock. It is a light clock. Okay, this has got a light pulse which is emitting from the front mirror and it is reflecting the back mirror. So here is a tick and there is a tock. Tick tock, tick tock. It is a nice way of going around. So this is a typical thought experiment which gives us an insight in understanding how light reflects. Two parallel mirrors are there and the beam of light is bouncing back and forth. And the time takes for the light to go up and down is basically the proper time. We say proper time by delta t or by delta t sub 0. It means the time that you just watch in your clock, on your wristwatch, on your Rolex. Well, I don't have a Rolex. So the light clock goes up and down, and each of this up and down basically measures a cycle. Now if I take the same tick-tock clock up and down which is going on, and if I make a object, the light clock, which is now moving at a fair amount of good velocity in the x direction. So just try to imagine if a tick happens over here, then the tock will happen over here, because I'm moving in the x direction. So again from this tock, if I further move, then the tick will happen over here. And from this tick again, if I move with this light clock, the tock might happen over here and the tick might happen over here, and it goes on and on and on. So this thought experiment helps us to understand that this delta t hash, the moving clocks run slow from an outsider's perspective because there is a time dilation. The further you move, you can see these lines become more and more curved. They go not in a straight line. And the delta t is basically the observer who is observing. For the observer, delta t is the same. It has got a tick-tock, tick-tock. Nothing great, nothing exceptional is happening. But for me, or for the outsider, delta t hash, this is something which is a weird phenomena. So I will take the tick-tock clock further and I will try to extend it a little bit more. That means we are running close to the speed of light, and here you can see the lines extend further. From this tock to tick, it takes further and further line. So the path is longer, obviously, compared to the stationary clock. The person seeing out from this particular frame of reference sees that the tick-tock happens at a lower rate. However, slower clock tick-tock means the times run on a moving clock, and the moving clock has a diagonal up and a diagonal down. It is not a straight line. So further you move, it actually makes further and further diagonal. And this actually solves our problem of what is called the twin paradox. So if Alice from the Earth is starting on a spaceship, is stationed over here, and Bob's fly away, you can see how these diagonal lines becomes longer and longer from tock to tick. So Bob is moving, Alice is stationed on the earth. When Bob comes back from this tick, what he finds is that Alice has become much more older, because the time for Alice is quite old, because you can see that these diagonal lines are further and further. So your biological clock, obviously, which runs at a nature's rate, your heartbeat, your aging, your other factors of genes, everything slows down relative to a stationary clock. So this actually shows what is called the tick-tock kind of an analogy for time dilation in special relativity. Now, what happens in case of a general theory of relativity? We will continue with this tick-tock, but what we will see is that this tick is happening over here, and the talk, instead of moving in a straight line, now we are following a curved path. It can be a curvature of a black hole, it can be a severely distorted space-time, you can think of anything. So here what happens from this tick to talk, you can see that it takes a long time, and further from this tick talk, the next tick happens a little bit low, because the more the gravitational field, the further is the stretch. So this path is longer, remember, not due to velocity, it is due to the curved space-time. So the person who has got a proper time, dt, is measured by a distant observer, whereas d tau, and you will see this tau is happening in the geodesic also, is a proper time actually experienced by a clock in gravity, and this is the deeper the gravitational field, the more stretch the photon's path and the slower will the time flow. So from here what we understand is that instead of motion, we have a space-time curvature affecting the photon's path. And remember, here also we are following the same analogy of tick-tock. So the dt is the proper time, and d tau is the proper time, and dt is the time measured by a distant observer. So d tau is actually what is in the gravitational field, which is causing the curve. And from here what we can see is that if you get a black hole, an extreme curvature, astronaut who is falling over here, actually the time is ticking perfectly. But here a tick happens here and a talk happens over here. So you can see due to extreme curvature, it takes a longer and longer time, and this person who is outside the event horizon sees that time slows down. So remember, in special relativity, time slows down due to speed. General relativity, time slows down due to curvature. So this is another misconception which might happen. This is a nice illustration, a rubber sheet, and an ant is following a path, and just due to curvature, you can see there is a paperweight and there is a sufficient curvature. And this leads to two important events or phenomena which happens in relativity. One is called gravitational redshift, and this occurs when a light source moves away from an observer and the wavelength of light stretches, shifting towards the end of the spectrum. And the second one is called blue shift, occurs when a light source moves towards an observer and the wavelength of light compresses, shifting towards the blue end of the spectrum. So as we have seen the Lorentz factor, here also in gravitational time dilation, the equation more or less is the same. Here you can see the time is slower because near the Earth's gravitational field is stronger. So what we get from here is this kind of an equation where this delta t hash is basically time experienced by someone closer to the massive object. You can think analogous to moving frame in special relativity. Delta t again is the time experienced by far away observer. You can be analogous to observer's frame in special relativity. M is the mass of the object, g is the gravitational constant, c is the speed of light, and r is the radial distance from the center of the mass. Now this would require a little bit of explanation which I will cover in the next video. What do we mean by radial distance? Because this is not the general distance which happens. We will explain that later. So here you can see that near a massive body, now we have explained, you can take that light clock tick-tock kind of an analogy, and you see that how things get stretched, and that is why times run slow. So here is the final outcome, that clocks tick slower near stronger gravitational field. So here are some of the misconceptions and the right concepts. Some people think that time dilation is just an illusion, which is not a fact. Experiments, for example, muons in cosmic rays show that time actually slows down. The traveler experiences time slowing down for themselves. You might think that your wrist clock, which can be either a HMT or a Rolex, is actually slowing down. The fact is that no, in your own frame, when you're looking at your clock on your wristwatch, it is only when we measured the experience normal time. Only when we are measured by a stationary observer, their clocks appears to be slower. There is another misconception which tells gravity slows down because it physically affects the clock. No, it is just the result of the curved space-time. Clocks follow the geometry which we have just seen. Some people think that gravitational time dilation is only noticeable near black holes. The fact is that no, even on Earth, gravity causes time to pass slightly slower near the surface compared to higher. We cannot see this because we need to have those kind of extreme conditions. So the effect is actually measured with precise atomic clocks. Some people also think that if time slows down in a gravitational field, people living there will notice it. No, local observers never notice it because they experience time passing normally. The tick-tock which happens on your wristwatch. So the effect is only noticeable when comparing clocks at gravitational potentials. People also think that only moving clocks run slower. The fact is no, in general relativity, even stationary clocks in gravity run slow due to space-time curvature. So from here we get two important conclusions. One is just like velocity-induced time dilation in special relativity, gravitational curvature bends time in general relativity, and more the curved space-time is stronger the gravity, the longer it takes for an event like a tick-tock, which we just have seen, to be completed. Well, that's all for today's video, because there has been a lot of other concepts which I wish to make it. But first, let me know, how do you like this video? Thank you very much for watching. If you have liked this video, please do not forget to click on the subscribe button and click on the bell icon to get all the notification from Physics for Students. You can go to my other channel, General Relativity Explained, where I have already started explaining few more concepts on general theory of relativity and related areas of physics in a much more detailed and a systematic manner. And you can always contact me at this email ID, which I keep on answering to all your email queries. Thank you very much, and we will be soon back with few more videos. Goodbye.